Okay, we figured out how to show kind of the electron configuration and how it builds as we go out. And this time what we're going to look at is we're going to focus on one specific type of electron, the valence electrons. Remember, the valence electrons are the ones in the outermost ring. Why the valence electrons? Because those are the things that make everything happen. Those are what's involved in keeping all matter together, forming chemical bonds. That's what keeps you in existence, not just a whole bunch of atoms floating around independent. So we focus on that because that does a lot of stuff. We deal with that as the main piece of forming compounds. So what we're going to do is we're going to look at just the outermost electrons. So once again, I've got a series of pictures. And on all these, you'll notice that I've got the rings. In the ring, in this case, I've got one electron. One electron is in the 1s spot, so what we would consider 1s1. You saw that in your electron configurations. One electron means that's going to be hydrogen, so we're going to put it in place. Okay. This one, we've got two electrons. Well, two electrons, if you notice, they're both in the first ring, so that's helium. Now remember that first ring can only hold two electrons, so it is now completely full. Okay. When a ring is completely full, renders that element stable, unreactive. We give that the name of a noble gas. Okay, noble gases become very important. We'll see that in a few minutes. Okay, on the next one, if we look, notice this time I don't have anything in the 1s ring. Why? Because for us to be out here in the second ring, that means the first ring had to be completely full. And I'm not going to worry about that, just too many things to be looking at. But we're looking here, and there's only one electron in the second ring. First ring is full, okay, but there's only one electron there. Now, what element is in the second ring has one electron, or a 1s1? Well, the second ring, these are the rings. There's 7 rings. So if we're going to go through and look, the very first spot here, lithium, is in the second ring. It would have just one electron because this filled up the first ring, 2. Lithium has 3 electrons. The first 2 went into the first ring. Now the third one has to start the next ring. Keep that in mind. That's something we're going to keep coming back to. Now if we look at beryllium, in this case, in the 2s electron, we've got 2s sublevel, we have 2 electrons. Okay, remember the s can only hold 2. And if lithium is 1 electron in the 2s, beryllium is 2. So they probably should go side by side. There's my 4 electrons. Remember the 2 on the inside, first ring, have already been accounted for. If we look at the next one, now I've got 3. Now notice I've moved into the 2 piece and I have 1 electron there. I'm still building that second ring. Remember, this is the second ring. So, and if we look, actually, take that back. There's 2 electrons plus 3 more is 5. So that's going to be atomic number 5, which puts us over here at boron. So move on to the next one. And once again, I'm just adding 1 electron each time. So you're seeing I've got different, we're following that pinkish orange one around. Okay, 2 plus 4 is 6 more. Notice in the second ring, I've now got 4 electrons. There's 4 valence. Keep track of your valence. Those are the important ones. So I'm going to put that over here with carbon. That's what it is. Pick up nitrogen. Well, nitrogen, number 7. Remember, 2 of them are in the first ring. So 7 minus 2 is 5. That means there should be 5 valence electrons. So let's see if we were right. 1, 2, 3, 4, 5. So notice in the second ring, there are 5 electrons. Okay. Maybe you're seeing a pattern now. Maybe not. Who knows? Okay. Going to the next one, oxygen. Well, if it's 5, then probably going to be 6. 1, 2, 3, 4, 5, 6. 7, 8 from the inner 2. Going through. Put oxygen in place. You can probably take a wild guess on the next one. 1, 2, 3, 4, 5, 6, 7, 8, 9 from the inner 2. So that's going to be our fluorine. And let's bring in the last one. And if you look at this, 1, 2, there's our 2 S's. 1, 2, 3, 4, 5, 6. There's our P's, because remember in the P sublevel, there's 3 boxes, and each one held 2 electrons. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. There are no more open spots in that second ring. Okay, that ring is now completely full. And when an element has a completely full ring, it's now unreactive, it's stable. Okay. Noble gases are naturally stable, and neon is a noble gas. Let's look at the next one. Coming through. And once again, notice I don't have anything in the first or second rings because we filled those up. And I'm only worried about the outermost rings, the valence electrons. Neon filled up the second ring. So we've got 1 electron in the third ring. Well, 1 electron in the third ring, well, the ring 1, ring 2, ring 3. Sodium is our first one there in that ring. So I'm going to just go out on a limb and say, hey, you know, sodium probably goes here. But I also have some logic to it. And the fact that hydrogen, which is right here, had 1 valence electron. Lithium, which is right here, had 1 valence electron. Sodium has 1 valence electron. So with that, you might start seeing something. Okay. If we were to take a wild guess as to what potassium would be, well, 1, 2, 3, it starts the 4th ring, and it's the first spot in. So it would actually have 1 valence electron as well. Pull up this one real quick. And we look, we've got 2 valence electrons in the third ring. There's my 3s2. And if we look, beryllium had 2 valence electrons. So in its outer ring, it had 2. Magnesium has 2 in its outer ring. So it probably makes sense that calcium, strontium, barium in that would also have 2. So we're seeing patterns as we go down. They have the same number of valence electrons. If we were to carry that over, aluminum, if that's all 1, that's all 2, aluminum should be the same as this, which is 3. Carbon's 4, so silicon, germanium in that should be 4. There's 5, 6, 7. There's 8. Now, these guys all have 8. Noble gases all have 8 except for one that I call the freak, helium. Helium only has 2. It ends in an S2. The reason helium is over here is because that first ring can only hold 2 electrons. Then it's completely full, which gives it basically the property of being unreactive, inert. It's a noble gas. But all the rest of these have 8 valence electrons. Helium's only 2, but they're full rings, which makes them noble gases. So hopefully that makes sense. Notice I've left this piece out so far. But I'm going to just show you one thing. You may have made the connection already. These guys are 1. These guys are 2. These guys are 3. Well, if this is the first time we get 3, these probably are going to have what for valence based on what we've talked about so far? Yeah, just the 2. And we'll come back to that more later. These are kind of special guys. Okay, so that's how we get our valence electrons. We also figured out the noble gases. Noble gases become important. We're going to do what we call shorthand notation. Because shorthand notation is a way to take electron configuration and focus only on those outermost electrons, the ones that have meaning. So with that, came up and I set this up. And these are things you already know how to do the electron configuration. We had a gizmo that walked us through that. Okay. Some of these tend to be quite long. A couple of you had a couple of them that you had to fill out, and it took a little while. Okay. I'm going to show you a quicker way to get them done. It's called shorthand notation. Shorthand notation, I care about the outermost electrons, but I also got to know where they're at. And in doing that, I need to know the noble gas. Specifically, I need to know the last noble gas, the noble gas that occurred right before the element we're talking about. So in the case of, let's say, Rb, rubidium, the noble gas that happened right before that, well, 37, 36 back over here, it's krypton. The noble gas that happened right before iron, just count backwards, 19, 18, so it's argon. The trick I use is I just go up one all the way to the end. Get you the same way, it doesn't matter. But those are the noble gases, and those symbols are what is important for us. So if we look, hydrogen's right here. What's the noble gas before hydrogen? Remember I said go up one all the way to the end or count backwards. Well, 1, 0, 0, there's nothing there. So hydrogen, there's no noble gas in front of hydrogen. So if I wanted to do its shorthand notation, let's actually use numbers. I would just write 1s1. That is its shorthand notation. I know, it doesn't save you anything. Now if we go to the next one, helium, there's no noble gas in front of helium. Go up one all the way to them, there's nothing there. So just like with hydrogen, its noble gas, or its shorthand notation, is its regular electron configuration. But now this is where it starts getting to where it actually helps. Go to the next one, lithium. There is a noble gas in front of lithium. Go up all the way to the end or count backwards, it's helium. Now here's the role noble gases play. We go through, and notice I've got these little brackets here. 1s2 is the electron configuration for helium. So when I go to shorthand notation, by typing in the symbol for helium, that's the equivalent of writing 1s2. That takes care of the inner ring. I'm only worried about the outer ring. Then all I have to do is type what's left over, what's outside of what I highlighted. Okay. On beryllium, beryllium's right here, up one all the way to the end. So it's going to be helium again. So helium's 1s2. Okay, I highlighted too much, sorry. So again. I just write 2s2, which is all that's left over. Because remember, by writing He, that's the equivalent of writing the 1s2. Now, if you look, all of these are running the same thing, and it makes sense because all of these elements have helium as the last noble gas. So every single one of these, I didn't put them all, but boron and carbon, you'll see why I didn't put them all in a second, have He, have the helium. So that's the equivalent of writing that. Probably should have highlighted that. So now this is where shorthand makes it a little bit easier. Now we just have to write whatever's left, or copy paste. So it saves us a little bit of time, especially when you can copy paste the whole thing. Ooh, sorry. I just skipped a few of them in there because all of these are going to end up having HE in brackets. Now, let's go to neon. For neon, I need to figure out its noble gas because I need its shorthand notation. Now, yes, neon is a noble gas, but we have to look at what the last noble gas is, the prior noble gas. And once again, it is helium. So for neon, we're still going to be doing HE in brackets. And then, once again, that takes care of this piece. Now we have to cover everything else, all the valence electrons. That's what we're accounting for. So this would be shorthand notation for neon. Have we really saved much? No, not really, but we will. Now let's go to sodium. Sodium's sitting right here. Remember, we started a third ring. It's the first electron in the third ring, so it ends in a 3s1. But here's the difference. Here's where things start paying off. The noble gas right before sodium, up one, all the way to the end, is neon, Ne. So now when we go to do this, the thing that goes in brackets always will be a noble gas. Now I can put the symbol for neon. And neon up here had a configuration that went out to 2p6. So now when I put Ne in brackets, it's the equivalent of writing all that. So all I have left is that. Now you can see where shorthand notation kind of plays a part. Okay. Mg, once again, it's just going to be 3s2 because the 2p6, that's going to be for neon. Now, argon. Argon's right here. Okay. I need to go to the last noble gas, the prior noble gas. So it's still working off neon. So it's always the prior noble gas. Now I take everything else. I should put Ne in here. There we go. Okay. So we're saving a little bit. Let's go to the very last one I set up, potassium. Potassium's right here. Okay, 1, 2, 3, it's in the fourth ring. Okay, there's one electron there. Find the last noble gas. Well, up one, all the way to the end, so it's argon. So now, if we look, argon ended in a 3p6, and we'll go back and look at that in a second. Yeah, orange sounds good. Okay, 1, 2, 3, that's a p. It's a p6. If you haven't figured out, these are all your p's. We've already talked about that, but there's just a refresher, p6. So there's our 3p6. All that's left, put AR in brackets, sorry. And then all that's left is this. And definitely now you see where shorthand plays a part. Okay, that's a basics on shorthand. We will get more in depth, more advanced, and you see where it pays off a little bit more. But hopefully that should help show you how to go from electron configuration to shorthand. Then we're going to go from shorthand into a concept called Lewis dot, and then we'll add to that. There you go.